All right, in this video, part 2, we're going to talk about conductors. Conductors are materials that have free electrons that are able to move around, jump between molecules, rush all together in a flow that we would call a current. The contrast to dielectric materials is that in a dielectric material, you may have charges build up, particularly at boundaries between materials, but that's what we call bound charges or a polarization charge. It is not free to move around, and we cannot make currents with those charges. And so when we talk about materials that can generate current, a dielectric doesn't count, but a conductor does. And so we're going to talk about how a conductor reacts. However, it should be noted that we can see that there is some parallel between dielectrics and conductors in that both do have some way to generate charges. And we are going to see later on that there is a connection between dielectrics and conductivity, even though the way we consider it here, they're sort of polar opposites of each other. All right, so this was our perspective of a dielectric material. A conducting material has basically free electrons that are not attached to a molecule, that are free to move around. And so the moment you place an electric field on this material, the electrons are going to be pushed in the other direction. Right? Now, it doesn't just have to be electrons. It could also be positives, right? It could be positive ions that have a positive charge. That could be a molecule with the electron removed, for example, that has a positive charge, and that's going to move in the direction of the electric field. In practice, however, most electric currents are dominated by electrons and not by ions. Electrons are much lighter than anything else, including protons, including molecules, and therefore ions. And so electrons tend to dominate most electric motion. So I'm going to cross out the ions only because in practice they're not important, but in reality, ions can create current and respond to electric fields just the same way that electrons do. All right, now the number of free electrons that are sitting here is very important because that's going to tell us something called the conductivity. All right, so conductivity is connected to the number of free electrons per unit volume. The more free electrons you have available, the bigger response you're going to get if you attempt to place an electric field on this material. All right, because the moment you place this electric field right here, you've got electrons that are streaming downwards. If there is an ion, it's going to move that way, and that's going to give us charge separation. Eventually, we're going to get negatives building up down here, and we're going to get positives building up down there, and that's going to create an electric field, a secondary electric field. It's going to go from positives to negatives. And as you can see, that secondary electric field is going to work to counteract the electric field that we have tried to impose on the material. And in a very good conductor, in fact, this secondary electric field is going to be so good that it completely cancels out the electric field. Now, the way we characterize the number of these free electrons that are available is with conductivity. Right? That is a material-dependent property. You can look it up in textbooks and research papers and tables, and you'll see a property called sigma, which has units of Siemens per meter, where a Siemen is basically a 1 over ohm, or sometimes it's written with an upside down omega, or sometimes it's a mho, MHO, which is ohm backwards. People seem to have a sense of humor about this. So that's the units of conductivity is Siemen per meter or mhos per meter, or 1 over ohm meters is also one way to do it. So typically for metals in particular, the value of the conductivity is very high. Right? So for example, sigma tends to be about 10 to the 6th, or 10 to the 6th to 10 to the 8th. Fix this. 10 to the 6th to 10 to the 8th Siemens per meter for metals. Right. This is a very high conductivity. Not infinite conductivity, but it's pretty high. things like copper, aluminum, silver will all kind of be in this range. And these are very high conductivity materials, right? Silver, steel. And so we would call these good conductors because they are good at conducting currents, or they also have very low resistance. If you place the voltage across it, you're going to get a pretty good current sweeping across it. All right. Now these sigmas are very high. To start out with, we're going to deal with cases where sigma is basically equal to infinity, right? The conductivity is so high that practically speaking, there are infinite number of free charges available. And the reason why we do that is that metals tend to act a lot like that. They have a conductivity that's high enough that it can be almost treated as a perfect conductor. But if sigma does equal infinity, then this is called a perfect conductor. So for today, we're going to strictly consider materials for which we can approximate sigma as being infinite. All right. Now, there are certain rules that are going to apply anytime we have a perfect conductivity. All right, so here I've got some little amorphous blob of material that's all, let's say, steel. So this basically has a sigma that's very big, a very big conductivity, lots of free electrons. All right, so the moment you try to apply an electric field anywhere within this object, you're going to have you're going to have the electrons move around, and you'll have quick currents that are going to respond, and they'll quickly rearrange into such a way that the electric field is killed. Because if there's any remaining electric field, it's going to be moving more of those free electrons, and eventually it won't stop until there's no electric field left. So the rules for a perfect conductor is going to start out with rule number 1, E equals 0 inside the conductor. Because again, if there were any electric field, then it's going to be pushing around electrons, and that process will never stop until there's no electric field to push around those electrons. And so by definition, we've got to get the E equals 0 inside the conductor. All right. Rule number 2, which is a corollary number 1, is that charges will build up at the surface only. Charges will build at the surface. And in fact, these charges will be precisely the right amounts to create E equals 0. So we may get positive charges over here. We might get negative charges over there. It's not necessarily going to be constant. The charge density will not be constant, but there will be charges that build up around the very edge of this conductor. And that arrangement of charge is going to be precisely sufficient to give us E equals 0. All right, the third rule is that the electric field is perpendicular to the surface, at the surface. All right, so while we can confidently say that right here, the electric field equals 0, just outside the boundary, it is possible that there will be an electric field that looks like this. Right? There could be an electric field that looks like that. And if we look at this top side here, where I've drawn a bunch of positives, we know that positives are going to be sources of electric flux lines. And so we can draw something like this, as long as all the lines that we draw are perpendicular to the surface. This will make a little more sense later when we talk about voltage and potential. But long story short, if the electric field line just outside the surface has any component that's parallel to the surface, then we're violating the first 2 rules, right? Or in particular, the first rule. All right. So as an example, I'm going to introduce you to something called a Faraday sphere or Faraday cage. All right. And so let's imagine we have this shell. It's a hollow shell, but the shell is made out of metal. Right, so this is a spherical shell as I've drawn it. And let's say outside of this shell, we've got a very big positive charge sitting right there. Right? We know the field lines from this positive charge are going to be streaming outwards, and so do the electric flux lines, D. Right? And these lines, though, are going to be set up in such a way that we have E equals 0 inside this conductor. So what ends up happening is, okay, this line will continue straight and hit this conductor, but this line is going to have to bend around and strike the conductor at a perpendicular angle, right? So this is sort of the motion of these field lines we're going to have to get in order to ensure that field lines strike this metal boundary at a 90-degree angle. All right. The other thing that's going to happen is this positive charge is going to draw a bunch of negative charges to the left, right? Those negative charges are drawn toward the positives. At the same time, the positive charges are driven the other way, so they're going to go to the other side of the shell. Okay? So the way we should view this is that this positive and negative charge is creating a secondary field. It looks like this, roughly speaking, and it will work out that this these secondary electric field will precisely cancel the field that would have been created by this positive Q charge. And so in the end, there is no electric field inside. When we sum up the electric field from the source with the electric field from the separation of charge, or you could say the polarization within this material, right? So this is called a Faraday cage. And it's a simple concept. It simply tells us that if you surround yourself with a good conductor, then sources from the outside cannot create electric fields inside that conductor. You could say you're shielded. Right? So the electric field equals 0 inside the interior of this Faraday cage. Right, so this is one way to, for example, create a room that's electromagnetically quiet, that doesn't have electric fields. Is just surround your room with a wall of metal, and you get a nice Faraday cage. So, for example, if when people are testing antennas for cell phones or for radars or anything else, they put them in a room that's lined with metal, so that any interference from outside, from power lines, from cell phone towers, doesn't get inside, and so you can sort of create your own natural test environment. Free from interference from the outside world or from other signals that you don't want as part of your test. All right. I'm going to show you an example of conductors in action. And I want to show you a little bit about how lightning works and how it connects to lightning rods. So here's a nice picture of lightning striking the Eiffel Tower in Paris. Maybe you've heard the expression, lightning never strikes the same place twice. And if you've heard that expression, it's wrong. It's completely wrong. I'll give you an example. The Empire State Building in New York gets struck something like many dozens of times per year. And that's natural when you've got sort of a metal structure going upwards. And this is basically a rudimentary example of what we call a lightning rod. Lightning rod is an intentional attempt to draw lightning into a certain location. And you might use that to protect something. So if you've got a building, one way to protect it is to have a bunch of lightning rods along the edge of the roof. In fact, if you walk out to lots of buildings on campus, including the building that my office is in, on the top you'll see these very small metal spikes that are maybe 6 inches or a foot tall, and those are designed to draw in lightning. So if lightning does strike nearby, instead of striking something that's bad, it hits these little lightning rods, and then you can sort of direct it away from the building and straight into the ground, and avoid damage to electronics and things like that. But let me show you a slow motion picture of lightning, and then I'm going to describe a little bit of the picture of how this works, since it relates to conductors and fields and all. This is a very, very high frame rate picture of lightning, or video of lightning that's taken. And this is the ground here. What you're going to see is something called a lightning leader that starts out above, just above this picture, right? There are clouds over the top of this picture that you can't see. And you're going to see a lightning leader work its way down toward the ground as it does so, it's going to divide up into segments and branch off. And although you can't see it, it actually proceeds in little steps. It steps forward, waits a little bit, then steps forward again, and waits a little bit. And eventually, here it is. One of those little leaders is going to work its way closer and closer to the ground, and it's finally going to reach the ground. At that moment, what you've got is a short circuit from cloud to ground, which are at very different electric potentials. And the only way to equalize that is with a very intense pulse of current. And that's called the return stroke of lightning. So this is a leader. And then watch when one of these little competing leaders strikes the ground, you're going to get a very intense pulse of current called the return stroke. So I'll play that video for you. There it is. There's the return stroke. If you observe this return stroke right now, you see it brightening and then darkening and brightening and darkening a few different times. So once this conducting channel is established, you can get repeated strokes that go along it. So if you've ever observed lightning to sort of flicker several times within a second, that's actually what you're seeing, is these repeated bursts of these repeated pulses of current going back up this channel from ground back up to cloud in what's called cloud to ground lighting. I'll show you this one more time. So there's the leaps coming down, and there's the return stroke. The return stroke, by the way, is can have hundreds of thousands of amps, so incredible amounts of current. The temperatures inside of this actual lightning return stroke can reach 30,000 Kelvin. That's significantly hotter than the surface of the sun, to put this in perspective. And it's so intense that it heats up the air, and the air has to expand, and that's what launches the thunder. So thunder basically originates from the lightning itself, and that's why they are, of course, connected. The sound wave from thunder, of course, travels much slower than light. So you see the lightning right away, and then after some amount of time, the thunder reaches you. But let me describe a little bit about how these leaders work, since it sort of connects to this idea of fields and conductivity. So in a typical thundercloud, you end up getting a very large separation of charges. And very commonly, you get lots of negative charge on the bottom, and you get lots of positive charges on the top. I won't get into the physics of why that happens, but suffice to say, it results from clouds that have updrafts within them and certain kinds of basically ice particles within it. And then so now you've got the ground, and now you've got the negatives. They're closer to the ground than the positives. So you're going to get an electric field typically from the ground going back up to the cloud. And this is what we might call our background electric field. As the charge separates in the cloud, you get this building up of this background electric field. And eventually, if it builds up high enough, you'll get a spark, right? A spark, just like if you rub your foot on a floor and then touch a metal doorknob, you'll get a little jolt and a little spark. And it takes a certain voltage, a certain electric field to break down air and convert it into something electrically conductive. And that's what a spark is. And once you get this spark, it has a way of self-perpetuating that I'm about to describe. And the way these leaders work is, let's say we've got a conducting channel right here. We've broken down air, and so air is now highly conductive. And because this is highly conductive, we're going to get a nice buildup of negative charges on the bottom of this leader, because the electric field is pointing upwards, and so negatives or electrons are driven downwards. All right. These negatives are in turn going to sort of force electric flux lines to go into them. Right, so the secondary electric fields that build up are going to sort of pop in to this tip right here. Right, so this is the E field generated by the tip. It's called an E field enhancement, because having this very sharp point with electric charge built up on the top creates a very high electric field over the top of it. And you can see that this electric field created by the blue basically adds up on top of the red. So the background electric field gets even stronger because of the presence of these electric negative charges in the bottom. And so what that's going to do is it's going to break down the the air that's just ahead. And so we're basically creating a new spark that's just in the next segment, and then the leader is going to step forwards. And then these electrons are going to stream downwards, and they'll end up at the bottom of this new leader, and then the process will repeat. And so this leader steps forward in discrete portions, working its way down toward the ground. Eventually, as this thing nears the ground, you've got a lightning rod right here. And the lightning rod is going to have this leader coming toward it that's carrying negative charge. And so naturally, you're going to get a buildup of positive charge at the tip of the leader. Sorry, at the tip of the lightning rod, as that negative charge is coming closer and it's drawing positives up. And again, this creates a very big enhancement, since this is going to tend to create electric field lines that look like that. And that just adds up and intensifies the background electric field. And so now, eventually, you're going to get a process called connection, which is where you get a complete electrical connection from the leader to this lightning rod. And because the lightning rod is sort of elevated, it's up in the air and it's very small, like needle-like, it's very easy to have a very intense enhancement of the electric field, and that's where this lightning leader tends to be drawn to. So that's how lightning rods basically suck in lightning, because the lightning basically wants to go where there's lots of charges to meet it, and any sort of point or tip of metal will do that. A sharp spike of metal will focus charges much better than a sort of a wide, a wide pole, for example, where the positive charges would be more spread out. So that's why lightning rods tend to be very thin, sort of needle-like. All right, so hopefully that was a little bit of an interesting perspective on conductors and how they work and relating to lightning protection and lightning rods. With that understanding of the way materials respond to electric fields, we can next move on to understanding the nature of how electric fields and charges relate to each other as well. And that'll be in the next lecture.